Beneath the sunlit surface of the ocean lies a realm defined by crushing pressure and absolute darkness, a world where humanity is entirely blind and must rely on sound to see. In this abyss, acoustic waves travel vast distances, carrying the whispers of tectonic shifts and the calls of the deep. Yet nothing in the recorded history of marine acoustics prepared researchers for the sheer, earth-shaking power of an anomaly that tore through the Pacific depths. It was a noise so profound, so impossibly loud, that it defied every known parameter of the natural world. The moment of detection occurred during the austral summer of 1997, deep within the remote equatorial waters of the Pacific Ocean. Researchers monitoring automated data streams were suddenly confronted with a signal of terrifying magnitude. It was not a localized event, but rather a sprawling acoustic footprint that washed over sensors separated by thousands of miles. For a brief, baffling minute, the ocean roared with an ultra-low frequency voice that belonged to nothing in the scientific catalog. To comprehend the scale of this event, we must understand the instruments that captured it. The National Oceanic and Atmospheric Administration, widely known as NOAA, operates a sprawling network of underwater listening devices called hydrophones. Originally developed by the United States military during the Cold War to track enemy submarines across global waters, the Sound Surveillance System, or SOSUS, was later repurposed for civilian scientific research. These highly sensitive titanium-encased microphones sit suspended in the deep sound channel, an oceanic layer where temperature and pressure conditions allow acoustic waves to travel across entire hemispheres with minimal loss of energy. When NOAA scientists retrieved the data from their autonomous hydrophone array in 1997, they isolated a sound that was immediately christened with a deceptively simple name: the bloop. The raw audio, sped up 16 times to be audible to the human ear, resembled a massive bubble rising from the seabed and popping at the surface. But the raw data told a far more intimidating story. The anomaly was an ultra-low frequency sound, meaning its acoustic waves were incredibly long and deep and its amplitude was staggering. It was the loudest unidentified noise ever recorded in the world's oceans. The initial analysis of the data yielded a deeply unsettling hypothesis. A spectrogram is a visual representation of the spectrum of frequencies of a signal as it varies with time, essentially a fingerprint of a sound. When acoustic experts at NOAA examined the visual footprint of the 1997 recording, they noticed a rapid variation in frequency. This specific type of sweeping, undulating acoustic curve is a hallmark of marine mammal vocalizations. The data looked undeniably biological, suggesting a living creature had produced the call. However, the biological hypothesis immediately collided with the hard limits of physics and biology. For a sound to be detected by multiple hydrophones spaced over 3,000 miles apart across the Pacific Ocean, the sheer acoustic energy required is astronomical. The blue whale, the largest known animal to have ever existed on Earth, tops out at around 100 feet in length and can produce calls reaching 188 decibels. Yet the 1997 anomaly was exponentially louder than the most deafening cry of a blue whale. If the biological signature on the spectrogram was accurate, it implied the existence of a marine leviathan of impossible proportions. A creature capable of generating such an immense acoustic wave would need to be several times larger than a blue whale, lurking undetected in the abyssal pelagic zones. This deduction captured the public imagination, transforming a rigorous scientific mystery into a modern myth. The idea of an unseen colossal organism dwelling in the uncharted depths fed into our primal fear and fascination with the unknown ocean. While the public dreamed of sea monsters, the scientific community rigorously pursued alternative explanations. Researchers hypothesized that the ultra-low frequency sound might be the byproduct of classified naval operations, perhaps a new type of submarine propulsion system, or a massive underwater detonation. Others looked to the geological volatility of the seafloor, suggesting that a sudden volcanic eruption or an uncharted hydrothermal vent might have produced the anomaly. Every known source of deep ocean noise was placed on the table and methodically compared against the 1997 data. The process of elimination in marine acoustics is a painstaking endeavor of comparative analysis. Geologic events like underwater earthquakes, known as seismicity, produce distinct acoustic signatures. An earthquake typically registers on a hydrophone as a chaotic, broadband crash of noise, lacking the smooth, sweeping frequency changes seen in marine mammal calls. Volcanic harmonic tremors, while more sustained, also fail to exhibit the specific rapid frequency sweep that characterized the mysterious recording. When researchers overlaid the spectrogram of an underwater earthquake onto the spectrogram of the anomaly, the mismatch was glaring. The tectonic grinding lacked the curved, almost organic rise in frequency that defined the mystery. Similarly, man-made noises from ships or seismic air guns used in oil exploration possess rigid mechanical regularity. The 1997 signal was fluid, dynamic, and singular. It lasted for approximately 1 minute, swelled in intensity, and then faded back into the ambient hum of the deep, leaving behind no secondary tremors or echoes. By the early 2000s, the investigation had reached a frustrating impasse. The sound had not repeated in any recognizable form, making it impossible to triangulate a precise origin point in real time. The autonomous hydrophones had successfully captured a ghost. The anomaly defied the geological, mechanical, and biological models of the era, standing as a verifiable anomaly in a discipline that relies on categorization. The ocean had spoken, but the vocabulary was entirely alien to the researchers listening. For nearly a decade, the enduring puzzle still loomed over the field of marine acoustics. The recording became a fixture in documentaries and scientific debates, often presented as the ultimate proof of how little we know about our own planet. It represented a fundamental gap in human knowledge, a stark reminder that the deep ocean, covering more than 70% of the Earth's surface, remained largely unexplored and deeply misunderstood. The silence that followed the 1997 event only amplified the mystery. The breakthrough did not come from a sudden flash of insight, but from a steady expansion of humanity's sensory network. In the mid-2000s, NOAA began deploying hydrophone arrays further south, venturing into the hostile, ice-choked waters surrounding Antarctica. The goal was to monitor acoustic activity in the Southern Ocean, an area historically devoid of long-term acoustic sensors. This new deployment was not explicitly searching for the source of the old anomaly, but it was about to provide the vital missing context. The Southern Ocean is a realm defined by the immense, grinding weight of glacial ice. Here, researchers began to record a high volume of previously undocumented acoustic events related to the cryosphere. They were listening to the sounds of icequakes, scientifically known as cryoseisms. These are non-tectonic seismic events caused by the sudden fracturing of glacial ice, or the catastrophic collapse of ice shelves into the sea. A cryoseism is an event of staggering kinetic violence, when a massive slab of ice, sometimes the size of a small city, shears off from the Antarctic mainland and plunges into the ocean. It displaces millions of tons of water. The tearing of the ice structure and the subsequent impact generate colossal shock waves. As researchers gathered more data from the Southern Ocean hydrophones, they began to isolate the acoustic signatures of these localized, catastrophic glacial fractures. The critical moment of unraveling occurred when acousticians at NOAA began to compare these newly recorded Antarctic icequakes with the archival data from the late 90s. The initial hurdle was one of distance and distortion. The hydrophones that recorded the original anomaly were stationed near the equator, while the new icequake data was being recorded at the source in the extreme south. Sound waves degrade and stretch as they travel thousands of miles through the ocean, altering their acoustic profile by the time they reach distant sensors. To account for this oceanic distortion, scientists applied complex acoustic modeling to simulate how an Antarctic icequake would sound after traveling over 3,000 miles to the equatorial hydrophone array. When the models were run, the resulting spectrogram was a revelation. The simulated long-distance cryoseism matched the 1997 recording with stunning precision. The amplitude, the duration, and most importantly, the baffling frequency sweep all aligned perfectly with the physics of fracturing ice. With the acoustic profile finally decoded, researchers could definitively trace the origin of the sound. By calculating the slight differences in the arrival times of the sound waves at various hydrophone stations across the Pacific, they triangulated the source. The epicenter was located in the remote depths of the Southern Ocean, likely near the Bransfield Straits or the Ross Sea off the coast of Antarctica. The mystery was no longer a question of what, but of how ice could mimic life. The explanation for the biological-sounding frequency sweep was found in the physical mechanics of the icequake. When a massive iceberg calves and scrapes against the jagged, uneven ocean floor, it creates a phenomenon known as ice tremor. The friction of billions of tons of ice dragging across submarine ridges generates an undulating, sweeping acoustic wave. As the ice block slows or accelerates against the seabed, the frequency of the sound rises and falls, perfectly imitating the vocalizations of a living creature. The sheer volume required to reach the equatorial sensors was facilitated by the SOFAR channel, the deep sound channel. When the icequake occurred, the resulting acoustic energy was trapped within this specific layer of water, where the speed of sound is at its minimum. Instead of dispersing vertically and losing power, the sound waves bounced horizontally within the channel, traveling thousands of miles with remarkable efficiency. The ocean itself acted as a massive global amplifier for the dying groans of the Antarctic ice. The confirmation of the icequake hypothesis marked the end of the Leviathan theory. There was no colossal, undiscovered monster lurking in the abyssal zones. Yet the resolution of the mystery did not diminish the awe of the event, rather it redirected it. The verifiable reality was that natural, non-biological forces on our planet were capable of generating energy on a scale that dwarfed the mightiest living creatures. The Earth itself was the Leviathan. The unmasking of the anomaly had profound implications for our understanding of global climate dynamics. The 1997 recording was not an isolated freak occurrence, but an early, exceptionally loud warning shot from a changing environment. By identifying the acoustic signature of massive ice calving events, scientists developed a new, passive method for monitoring the stability of the Antarctic ice shelves. The hydrophone arrays could now be used to track the rate of glacial deterioration from thousands of miles away, providing critical data on ocean science. This revelation fundamentally altered the paradigm of marine acoustics. The deep sea was once thought to be a realm of serene, eternal silence, occasionally broken by the calls of whales or the distant rumble of an earthquake. The icequake explanation proved that the ocean is a dynamic, violently active acoustic environment. It is a place where the shifting of continents and the fracturing of glaciers create a constant, ultra-low frequency symphony that we are only just beginning to comprehend. The journey from a baffling acoustic anomaly to a verified natural phenomenon stands as a testament to the rigorous, self-correcting nature of scientific inquiry. When faced with data that defied explanation, researchers did not default to the supernatural or the impossible. They expanded their sensory networks, gathered new evidence, and applied rigorous comparative analysis until the mystery yielded to facts. The lessons from that initial investigation never faded, reinforcing the necessity of patience and empirical observation. While the specific enigma of the 1997 recording has been solved, the sprawling hydrophone networks of NOAA continue their silent vigil in the dark. They monitor an ocean that remains vastly unexplored, a fluid frontier that undoubtedly holds more anomalies, more unexplained data points, and more astonishing truths. The deep waters are constantly speaking, vibrating with the immense forces of a living planet, and we are left to wonder what strange, verifiable phenomena the next great sound will reveal.